let me start by of course, thanking the organizers for inviting me to this great conference, this amazing place. It's my first time here and the first time in Korea, so I'm very happy to be here. And talking about some of our work that I guess emerged over the last, 2 or 3 years. So me personally got involved kind of looking at these classical spin systems during my postdoc while I was, do I have to change the presentation slides or will that just happen?
Just 1 second. Yeah, we will.
Okay, there they are. Okay, and that's my pointer. Great. So I got involved thinking about this during my my postdoc at MPI in Dresden. And this is work together with Adam, who's a PhD student on the project, and Masoud and Roderich, both at MPI. And I'm now at OSU Oklahoma State. And this is work on 2 works. One is published and the other one is on arXiv now, hopefully soon also published. And so let me start by discussing why I personally think that kind of spin systems are interesting and also classical spin systems are very exciting. So I personally kind of worked originally on kind of classical chaos and out-of-time world commutators in classical spin systems in the context of chaotic spin liquids, but also in the context of kind of ordering ferromagnets or antiferromagnets. And it really was motivated at the time by kind of this emergence of OTOX as a quantity for quantum chaos, and then thinking about a system like spin systems where it's a very clear classical limit, what these quantities actually mean in a classical context. So it's one of the things we kind of were thinking that's a very kind of interesting contribution in that field, using a classical many-body system to understand kind of many-body chaos. Of course, there's also other people that work kind of with classical spin systems. Another thing that I found kind of very exciting in recent times are these time crystalline phases. And also those have now been established in a slightly different way in terms of pre-thermal phases, also in classical spin systems. There's actually a variety of things that one could have thought are purely quantum that are now established also in classical spin systems. So you can also kind of look at kind of kinetic constraints in the context of, say, fractons or many-body localization or scarring. And similar phenomena can also show up in classical many-body systems. You can even kind of define something like measurement-induced phases, which you could have thought are very quantum, but you can actually also define a classical version of that. They kind of find similar phenomenology for critical transition between kind of a spreading phase and kind of a localized phase. And then the topic of this talk will kind of be about hydrodynamics, integrability, and KPZ scaling in the classical Heisenberg chain. So the topic of this talk is going to be non-equilibrium dynamics, and to kind of give a very brief introduction. Why is kind of non-equilibrium interesting? So generically, of course, many-body systems are very complex. Dynamics is even more complex than equilibrium processes. However, in many cases, kind of nature is kind to us. We don't have to understand everything. In some cases, there are kind of universal concepts that emerge that don't actually depend on the microscopic of the specific system. And that happens in equilibrium, which kind of allows us to define what the phase is. It also happens out of equilibrium in the sense that there can be dynamics that actually doesn't depend on the microscopic parameters of your theory. So these are kind of 2 examples from the quantum world that are related to what I'm going to talk about. So those are kind of 2 experiments where you kind of look at a spin system in 1 dimension, and you can kind of ask how do either local fluctuations of, say, a magnetization spread out over time, or you can ask how does a domain wall, where kind of the left one side is up, the right side is down, kind of spread or kind of melt in time. And it turns out that in this case, which are kind of 1D XXZ models, those don't spread diffusively. There's kind of a different universality class, which is the KPZ or Kata-Parisi-Zhang universality class, which originally kind of described surface growth, but kind of has turned out to describe kind of a variety of other kind of dynamical processes. In particular, it describes this quantum XXZ chain, and it also describes some classical chains, in particular kind of the integrable Ishimori chain. And I will argue in this talk that this behavior that you would have thought is kind of very special, that kind of relies on integrability, can even happen in the, what I would call the most generic, most simple model of kind of spin dynamics, which is the 1-dimensional classical Heisenberg chain. And why is that surprising? So basically, if you kind of think what should happen at long time scales or length scales, the theory you would use is hydrodynamics. And the basic idea is that instead of describing all the microscopic kind of quantities, you kind of go to large length scales and you only look at the dynamics of a conserved quantity at charge, and that will kind of evolve slowly. And at the most basic level, if you have a conserved quantity rho, then there's a continuity equation. So that should at first order only depend on the derivative of the current of that charge. And then in first order, that current itself should depend on the first order derivative of your conserved charge. And then there could be higher order terms. If you just assume those two things, which seem somehow very generic and unescapable, then you just immediately get diffusion out. So if these are kind of the underlying equations, then the 2-point correlators of your charge operators will kind of show diffusive scaling, which means they kind of follow a Gaussian scaling function with an exponent alpha of a half. So kind of a localized blob will spread diffusively over time to kind of a more delocalized blob. So more generically, this exponent could be different. It doesn't have to be a half, and the scaling function doesn't have to be a Gaussian. So it could also be, say, KPZ. There's a few ways to get around it. This is not kind of comprehensive. You can either use integrability, so then there's not only a few charges, but many of them, or you could kind of disallow the first order derivative and only allow higher order ones, which is what actually happens in Fracton models. So with that, let me kind of go through what I'm going to talk about. So the first part will be about kind of establishing this KPZ scaling in the classical Heisenberg chain. And depending on time, I will also show how we might be able to understand this kind of anomalous behavior in the Heisenberg chain in terms of solitons that actually appear in the ferromagnet case. So let me briefly introduce the model. So it's very simple. I'm going to look at the classical one-dimensional Heisenberg chain. So my degrees of freedom will be three-dimensional spins, Si, that are on the sides of a one-dimensional lattice, and they will only interact with the nearest neighbor with an exchange constant J. At high temperature, kind of the Hamiltonian will not matter, so the states will be purely random, so they will kind of point in random directions. Whereas at low temperature, kind of it will at least locally order, and if J is larger than 0, this is a ferromagnet, so all the spins will be aligned. If J is smaller than 0, it's an antiferromagnet, and those spins will enter-align on different sides. And again, that is of course only locally true, because for classical system 1D, there is no long-range order. And then we will have dynamics, which are essentially just precessional dynamics, which you can understand in terms of Landau-Lifshitz equations or a Poisson spin bracket. And to kind of give you an idea what that is, you could imagine I fix the boundary spins and then only asking what the central spin does. And the central spin will precess in the exchange field given by its two nearest neighbors. So it would kind of wind out this circle in the exchange field of their neighbors, which is kind of large gray spin. Of course, it isn't quite true because those neighboring spins are not fixed, so they also evolve in time, and that is why the dynamic is actually not integrable. So if you had asked me 2 or 3 years ago and asked me, is this model generic? I would have said, sure, it's one-dimensional, so it doesn't order, and it's many-body chaotic. So this would be the simplest generic spin Hamiltonian I could write down classically. And I'm going to argue that it's actually not as easy. So what we're going to looking at is now the question, what is the hydrodynamics of this model? And you could have thought, this is a very simple model, has been written hundreds of years ago down. Do we actually know? And the answer is we don't really know. So there are arguments that it should be diffusive because it's many-body generic and it's not integrable. There are arguments for non-diffusive behavior. There are arguments for logarithmic enhancements or 1/√T enhancement to diffusion. And none of those actually in our numerical results turn out to be true. So at least at low temperature, I'm going to show that actually this shows at least some regime of KPZ scaling and solitons, which we found very surprising when we kind of stumbled upon this in this most simple generic spin Hamiltonian we could have thought of. So what we're going to do is, so we're going to take the system. We're going to take, say, large systems of about 10,000 spins. We're going to sample an initial state from the Boltzmann distribution. Then we're going to look at our Landau-Lifshitz dynamics, evolve it to some final state. And we're going to ask what do the charges, the magnetizations, or the energy in this kind of system do numerically. So specifically, we're going to look at these 2 top-point functions. There's 2 quantities we're going to look at. One is kind of the energy correlation function, where we kind of have to subtract out the kind of expectation value. And the other one is the magnetization or spin-spin correlation function. And because it doesn't order, there's nothing to subtract in the case of the spin correlation function. And we're going to ask whether these kind of correlation functions at long times and long length scales collapse onto a universal scaling function in terms of parameter alpha and in terms of the universal function, a scaling function f. And the exponent alpha can equivalently also extract it directly from the autocorrelation function just by kind of looking at the equal time correlation function, which then should be a power law. So we are literally just asking, evolve, look at shaded magnetization, and ask how does it diffuse in time. And let me start with the results. So this is now numerics. We're kind of looking first at the case of the energy, and we're going to fit that to kind of a simple Gaussian scaling function at, say, intermediate temperature, but this is true at all temperatures, both in the antiferromagnet on the left and the ferromagnet on the right, as a function of a diffusively scaled distance and a diffusively scaled two-point function. And those look perfectly Gaussian, kind of at all length and time scales. In principle, at all temperatures, so at infinite temperature, that's obvious. At low temperature, the ferromagnet also has ballistic components, but at long times, it becomes diffusive. The same thing is true for the spin correlation function. So now the correlation function is literally the two-spin correlation function. And again, at high temperature, we can kind of fit a Gaussian scaling function. And if you look at the autocorrelator, it's scaled by t², we see this perfectly converges to kind of a constant. And that tells you we observe no logarithmic anomaly. We also don't observe any other corrections. So this is perfectly diffusive. And the correlation function is a perfect Gaussian. So this is kind of exactly as we expect. Everything works out. It turns out if you look at the spin correlation function at low temperature, that isn't true anymore. So for the antiferromagnet at high and low temperature up here, it stays perfectly Gaussian. If I look at the ferromagnet at high temperature, it's also mostly Gaussian. But at low temperature, this exponent actually is very close to 2/3. So again, this is not a Gaussian now. This is a generalized Gaussian where I kind of take alpha 2/3 to get the best fit here. So this is all now a surprise. The ferromagnet doesn't look diffusive, even at these very long times. You can kind of look into that a bit more in detail. And you can kind of ask, what does the autocorrelation function do? And again, at high temperature, it's diffusive. At low temperature, it's very close to 2/3 for the ferromagnet only. And you can ask, okay, how does it involve kind of in temperature? So if I increase temperature at high temperature, perfectly diffusive. At low temperature, the best fit exponent is actually 2/3. And curiously, it's also the most straight line when I get to 2/3 exponent. And then finally, the question you could have asked, okay, you observe an exponent, is it just a drifting exponent? That doesn't tell me much. You could ask, okay, do I actually observe a KPZ collapse for that scaling function? So this is now a comparison for the low temperature antiferromagnet of the spin-spin correlation function versus a Gaussian, which is kind of this dotted line up here, and the actual KPZ scaling function, which is the black line here. And it's clearly inconsistent with Gaussian scaling function. It's perfectly consistent with the KPZ scaling function. So what we observe here is that the low temperature ferromagnet for extremely long times shows perfect KPZ scaling. I guess I might going to skip the equilibration. So you can ask, okay, this was equilibrium two-point functions. You can ask the question, is it also true for quenches? So specifically what we did is, imagine you start with an XY magnet at time equals 0, and then you allow Heisenberg interactions for time greater than 0, and you ask how do the observables relax towards this thermal Heisenberg expectation value. And it turns out that those are also, again, perfectly normal for the ferromagnet and anomalies for the antiferromagnet. So if you compare the scaling exponent for the antiferromagnet, for the ferromagnet as a function of energy, those also become anomalies at low temperature at the same point where the equilibrium exponent also were KPZ. So this is the same story, both in equilibrium and out of equilibrium. The ferromagnet at low temperature seems anomalous and it seems KPZ. So to summarize, what we found is energy correlations are always diffusive at all temperatures for both ferromagnets and antiferromagnets. The spin correlation function is perfectly diffusive at high temperature. There are no log corrections or anything else, but at low temperature, in the ferromagnet, it seems there's a long-lasting KPZ regime. And what I want to point out is, if I say low temperature, it's still in a regime where the correlation length is just a few lattice sites. So it's not that it's close to a continuum limit. It is still very much a discrete lattice model in this case, which was even more surprising to us. So with that, to kind of conclude, we find this long-lived KPZ scaling in the ferromagnet. And now we have to ask, where does it come from? And we were wondering, okay, could it be kind of the continuum limit? So we know the continuum Heisenberg model is integrable. So you could argue that's why you find KPZ scaling. The problem is this happens, as I said, in a regime where the correlation length is 2 lattice sites or 3 lattice sites. So really, it's very far away from any continuum limit you could think of. So what we now kind of came up with, which I will kind of discuss in the second part, is that is not close to the continuum limit, but it could be close to a different integrable model, which is kind of the second part that we'll discuss, and it will not show that not only does it have KPZ scaling, it also has long-lived solitons, which are typically kind of a signature of an integrable model. So to kind of put it into context, of course, as I said, the continuum Landau-Lifshitz model has solitons. There's actually an integrable version of the like Heisenberg model, which is called the Ishimori or integrable Landau-Lifshitz chain, which also has solitons. Generically, you would have thought the Heisenberg chain is non-integrable, so there shouldn't be any solitons. So that was our expectation, and I'm going to show that that doesn't quite work out. So this is the actual integrable perturbation of the Heisenberg chain. So instead of S dot S, you kind of have this kind of weird log interaction. And the way you get to that model is you essentially take a discrete nonlinear Schrödinger equation, which is known to be integrable, and you kind of map it to spin degrees of freedom, and then you get this model. And that's how Ishimori essentially, I guess, initially described it or discovered it. And then you can use everything you know from the Ablowitz-Ladik chain. You get the one soliton solutions, you get the two soliton phase shifts, and you get the full thermodynamics for free. And you also get the conserved numbers of charges, this tau I and higher order correlations. And that has been shown to show KPZ scaling. So there's classical studies of this model, and that shows, again, KPZ scaling. And it was recently shown that this KPZ scaling is also robust to symmetry-preserving perturbations. So as long as it preserves the O3 symmetry, this KPZ scaling seems to be pretty robust. And just to compare these two results, so I kind of claimed that we saw this KPZ scaling, but you might have thought, well, that's numerics. Was it really KPZ? So this compares our results for the Heisenberg chain to the best results for the kind of Ishimori KPZ chain. In terms of scaling collapse, the deviation in our case and their case above the noise level are essentially equivalent. So if you believe this is an indication of KPZ scaling, then you should also believe that this is an indication of KPZ scaling, at least for the timescales we looked at. So with that out of the way, let me kind of briefly kind of discuss the solitons we have. So for the Ishimori chain, we know them exactly. You can just write them down analytically, and that's kind of what they look like. They kind of have like a bump in the Z magnetization, and then they have a wave-like pattern in the XY components. And they're fully parameterized by two parameters like R and K. And R is essentially something like a width parameter, how big it is. So this R essentially determines the width of this kind of peak or bump. And the K is essentially something like a momentum. So this will determine both the velocity, how fast it moves, and how fast the kind of XY components rotate in plane. And I did have a video, but I think this is the PDF, so I might not be able to show this video. So this would just have been a video of a moving soliton. Oh, I can. So this is just a moving soliton of the Ishimori chain. And you could now ask, okay, I know all of these solitons exist in the Ishimori chain. Do they actually also exist in the Heisenberg chain? And what we did is we kind of showed that they actually do exist. So these K and R are these two parameters of the Ishimori chain. And the yellow region is where these solitons can be adiabatically connected to a soliton in the Heisenberg chain. So essentially in this regime, we have these solitons. In this regime, we don't find these solitons. That doesn't mean they couldn't exist, but we didn't find them. So the interesting thing is they exist for all WIPs, in particular at zero momentum, which I think wasn't known before. So we have essentially stationary solitons that we know essentially exactly. And at large solitons, so at large velocities, only white solitons actually turn out to be stable. So this phase diagram shrinks as you go to large momenta. And these are now not Ishimori solitons, these are now Heisenberg solitons. So these are now Heisenberg dynamics of these solutions we find, and you can kind of look at them for essentially numerically for infinite time. So we never see single solitons decay ever. So they seem to live forever. So the lower one is essentially just a longer time plot where we go up to, I think, 10,000 J, so 10,000 exchange times, and they never change. So with numerical precision, they're infinitely lived, at least the single soliton solutions. We also can find a construction for the stationary ones. So those we can actually make an ansatz for and essentially solve exactly. That gives us kind of a set of equations, which we can then, with a clever trick, kind of solve. And we can kind of go through that procedure, and that converges very fast numerically, and specifically, it actually converges exponentially in number of sweeps we do. So it's literally a contraction of this set of equations that exponentially converges you to an exact soliton solution. And then the second thing we did is for the moving ones, we adiabatically connect them to the Heisenberg model. So we now write down an interpolating Hamiltonian where we have parameter gamma, which for gamma equal to 1 is the Ishimori chain, and for gamma equal 0, it's the Heisenberg chain. So I start with gamma 1 at an Ishimori, and then I kind of tune with time the parameter gamma from Ishimori to Heisenberg, and I kind of evolve my single soliton solution with this interpolating Hamiltonian. So I start with Ishimori soliton, I change my gamma in time with kind of a time-dependent function, and I get my Heisenberg soliton out. And if this works, I've constructed a Heisenberg soliton that then I can evolve forever with the Heisenberg Hamiltonian without changing it. And if it doesn't work, so for kind of these kind of narrow, fast-moving ones, this fails. So what happens is the soliton will either break up or it will emit lots of pulses. And that was this regime in the phase diagram where I said I didn't have solitons. So that's how we constructed them. So that's all single particle physics. You can also now look at two particle soliton solutions. And what we find is if I kind of shoot in two solitons with opposite velocities, they kind of scatter, there's some interaction region, and then they emerge. And it turns out that for many of these solitons, they scatter almost ballistically and almost integrably, in the sense that I can scatter them not only once, but I can scatter them 100 times, 1,000 times, and they survive all of these collisions. So this is kind of a video of kind of the right plot, and you kind of see it just goes through and it really doesn't change. What you also observe is each time I hit the stationary soliton, it moves a few sides. So we literally see the emergence of something that we would call a phase shift into soliton collisions. And you can also compute that numerically, and you can compare to the Ishimori result, and the phase shifts we get are extremely close to the integrable case. And the final thing I want to say is, okay, we found one solitons, we found two solitons. The last thing I'm going to argue is also thermal states seem to be composed of many solitons in the Heisenberg chain. So what we're going to ask is, okay, the Ishimori chain is a soliton gas. So every state can be written as a superposition of many solitons. Can I do the same thing in the Heisenberg chain? And to do that numerically, we essentially take a state, a thermal state of the Heisenberg chain, and we're just going to kind of add vacuum around it and ask what emerges from my thermal state. And that's essentially what is kind of the inverse scattering method for integrable systems. We just do that numerically. So we have our solitons initially, and if we wait for a long time, they will just separate out, and we can count them. And that's what we kind of do on the left for the Ishimori, and on the right on the Heisenberg chain. So there's kind of a weird thermal mess of 100 sides on both sides. And then I kind of just wait a long time. So now I zoom out. So these are now 40,000 sides. And after a long enough time, I see kind of well-localized peaks, left Ishimori and right Heisenberg. And again, by eye, those are essentially identical, right? So after long times, what we see is that many localized peaks that emerge from a thermal state. So in that sense, what you observe is that the thermal Heisenberg state of the ferromagnet at low temperature seems to contain many solitons. Which then brings me to the final conclusion. We found one soliton solution that is stable to two-body scattering, and we found thermal solitons. And finally, what you can also observe, if you scatter a soliton through a kind of a stationary one, the magnetization of the soliton is screened as it moves through other solitons. And with this phenomenology, you can now use the same mechanism to get KPZ scaling from the quantum case also to classical case. So the idea is, as you have the soliton gas, solitons move through each other, magnetization gets screened. So that is, even though we have ballistically moving particles, we don't get ballistic spin transport because there's screening. But because we have these multi-soliton solutions that are long-lived, we actually don't get diffusive transport either, but we get KPZ. And that's kind of my summary. So what I'm hopefully convinced of is that even the most simple models you could think to write down, like the classical Heisenberg chain, hide a rich kind of area of kind of many-body physics. So specifically, I talked about kind of KPZ scaling at low temperature and the ferromagnet. And then I kind of tried to explain or motivate that KPZ scaling in terms of connecting it to the integrable Ishimori model, kind of showing that we find both one-soliton solutions as well as kind of many-body soliton solutions that kind of compose or that make up the thermal states. which then is one explanation how you could get KPZ scaling out. And what seems to be emerging is that even though these models are clearly non-integrable, they're many-body chaotic because they're close enough to an integral model and they preserve the SO3 or O3 symmetry that these solitons are extremely robust as long as you don't break that symmetry. And with that, let me thank Roderich and, of course, Adam, who did most of the work. I put down the references, and the contacts are me. Thank you for your attention.
Let's thank Thomas for a very nice talk. Questions? Yeah.
Thanks. So, am I understanding correctly then that the it's only in the ferromagnetic case that you get the KPZ and the solitons?
That's right. Yeah. So, I mean, you could think about why that is, because first of all, the equilibrium properties are, of course, exactly the same. The ferromagnet can be mapped to the antiferromagnet by just flipping every second spin, right? The thing is, that is not true dynamically. So the equations of motion are not invariant under that transformation. So that is why the ferromagnet can actually be different than the antiferromagnet if you look at dynamics. And then the other thing you could think about is, of course, the ground states are very different. So even though, well, it might not be the right description because, as we said, we are in a regime where the correlation length is 2 or 3 sides. So it might not matter that the ground state, you could imagine it's a smooth deformation of an equilibrium, of the continuum model. But I would actually argue that is not the right explanation. It's really that the Ishimori model is close by. And you could argue their design matters because there's this log 1 plus or 1 minus are very different. You can't just switch the sign in the Ishimori model. And that's, I would now say, is our explanation why the antiferromagnet is very different than the ferromagnet for this case.
Thank you.
Yeah. Okay. You can, yeah.
Hi. Hi. I wanted to understand if some of the things you can see could be due to pre-thermalization and not thermalization.
So, I mean, right, I mean, what do you mean by pre-thermalization? In the first part, right, we start from a purely thermal state. So those are exact thermal states of the Heisenberg chain that you can sample exactly. So the initial state was perfectly thermal. And then we just asked, what does the correlation function do? So I don't think there's a notion of pre-thermalization if I start from a purely thermal ensemble. Of course, the equilibration dynamics could have been in a kind of intermediate time regime. However, so if you believe, say, it's maybe KPZ for some time and then becomes diffusion later, the timescales, if you believe that, so imagine you do a fit where you say it's some 2/3 exponent for some time, and then it crosses over to diffusion a half at long times, then the crossover timescale that you could extract from our results is something like 10 to 7J. So you could, of course, say we can never exclude that at infinite time it becomes diffusive, but you have to wonder if that timescale is so large that for any system you could even find in nature that never happens. Sure, it's a finite time phenomenon, but if it's larger than the age of the universe, do you really care? But yeah, I agree. So none of our results show that this is an infinite time property.
Yeah.
A simple question. So this was partially addressed already. I was wondering if you change in the interpolation Hamiltonian, you go to negative gammas, and it becomes more like an antiferromagnetic case.
Right. So the first problem is that changing the sign in there is a problem because it's a non-bounded Hamiltonian. So the first problem is if you change the sign, then there's no zero temperature state. So that is one of the problems why you can't just do it immediately. The second thing is when we tried, the solitons actually broke up.
Okay. Yeah, but the reason I'm asking that, I was wondering if, so apparently your main statement is that Heisenberg model isn't really in proximity of the Ishimori chain. So I was wondering if you can actually tune the somehow make an interpolation that would make it clearer. So find a Hamiltonian that is sufficiently simple looking, but where, say, you can see the solitons disappear faster, or where you can basically see even a completely chaotic behavior. So did you try?
Right, so we tried a few different ways of doing it. So the one I showed is literally just going from Ishimori to ferromagnet, and that works in the way described. You can then ask, okay, if I was in the ferromagnet, can I somewhere interpolate to the antiferromagnet? And whenever we tried, it broke up. You can also ask what happens if I break the SO3 symmetry. In that case, they also break up pretty quickly.
Yes, but this is kind of a trivial break. Now, I'm really like curious, like what makes like what I had in mind is rather to see an interpolation where you start with the Ishimori chain, you pass through the Heisenberg Hamiltonian, and then you go further. But
right. So the question: how do you now interpolate from Heisenberg to what? To the from FM to AFM?
No, AFM, I guess, is too drastic.
So you want to go from FM to a different model? You can. So essentially, we also tried adding, say, second nearest neighbor couplings. That works as long as they're not large enough. So essentially, what we found is as long as we don't change the ground state to kind of a twisted spiral, so as long as it stays twisted spiral, we are fine. If you do something weird to the ground state, then things can happen. Yeah.
So you added the second nearest neighbor antiferromagnetic.
Yeah.
So second nearest neighbor ferromagnetic doesn't do much.
Right. Yeah.
Okay. Thanks.
Okay. Any questions? Yeah. So maybe I had a question. Regarding this solitons appearing both in the Ishimori chain and in the other one, you have all these emergent solitons, right? From those emergent solitons, can you compute something which actually you get the KPZ exponent?
Yeah, so that's something we wondered about. So the first thing is, so I'm not a full expert on the whole KPZ literature. So my understanding is that there is no rigorous calculation of the KPZ exponent for any model. So there are somehow hand-wavy physicsy derivations on how you get KPZ out for the fully integrable XXZ model, but they also rely on some approximations and saying, okay, we have the scattering phase shifts, we know what the multi-domain Wolf states are, and we assume this scaling for their collision rates, then we can hand-wave that we get 2/3. But as far as I know, there's no fully macroscopic, rigorous calculation to ever get KPZ out in any of these models. So we tried, but we would need to understand the multi-soliton scattering phase shifts better to do that. Yeah.
I even meant like numerically. Did you compute some distribution of weights or collisions?
Right, right. So what we did is we computed the two soliton phase shifts. So those we looked at numerically, and they look very close to KPZ with some numerical problems. It's a bit more involved. So we didn't look at two soliton kind of collision rates and the distribution of how large they are. So in principle, you could ask, what is the thermal distribution function is a function of R and K in a thermal state? We thought about it. We never computed that exactly because it might be statistically hard to get a good distribution function out. But that's an interesting question we were wondering about, but we never pursued it to the end. So that's an open question. It would be actually interesting or exciting to know if the distribution function is the same as Ishimori or very different in the Heisenberg case.
Right, yeah. Okay, thanks. Any more questions? There's a question on Zoom.
Okay, can I ask a question?
Sure. Go ahead. Please go ahead.
So for the KPZ scaling, you speculated the soliton may play some important role, right?
Yeah.
Then can you measure the soliton density in the ferromagnetic regime as a function of temperature? Is there some phase transition?
Yeah, so as I said, we haven't looked at it quantitatively. So I would imagine that something like that might be at the heart of it. The other thing we could imagine is that as you increase temperature, it could be that you either change the type of solitons you get. And as I said, the fast ones there's fewer of them, and most likely they collide more and would decay faster. So it could be that as you increase temperature, either the collision properties change, or it could be that the types of solitons you get, or it could be a combination of both that leads to the fact that at high temperature, the KPZ vanishes. Yeah, but we didn't look at it quantitatively, so I couldn't answer.
It's just a short question. How do you impose the temperature in your simulation? You do the deterministic dynamics?
So we literally just sample the full Boltzmann ensemble. So essentially, the initial state we take is E2 minus beta H.
The temperature only enters into the initial condition, but the dynamics is deterministic. Okay, thank you.
Yeah. So it's so you could ask, is it really a thermal ensemble? But in 1D, temperature and energy are exactly the same because we can sample it exactly. So that's easy. Yeah.
Okay, thank you.
Okay, any more questions? Okay, if not, let's thank Thomas again for the very nice talk.